So good afternoon, everyone. Welcome to the third lecture of this mini school on machine learning methods applied to high energy physics. And today we start the last cycle of two lectures on the basics of machine learning proper. Yeah. And our speaker is Dr. Pallab Basu, and I will ask Professor Jejjala to please introduce him.
So thanks. We're happy to see everyone here. I'm very happy to introduce my colleague, Pallab Basu. He's at WITS with me. Pallab did his PhD at the Thailand Institute for Fundamental Research in India, and he did postdocs at University of British Columbia and the University of Kentucky. He had a position at the ICTS in Bengaluru before moving to South Africa. So since he's been at WITS, he's been a wonderful colleague, and I've learned quite a lot from speaking to him. And I think he'll give some fantastic lectures on this topic. So please, Pallab.
Thank you. Thank you very much. Pallab, if you would like to share the screen, the floor is all yours.
Yeah, I'll share the screen.
Are you all right?
Yeah.
Yeah, okay. Excellent.
Can you see my slides?
No, we can see, I guess, your desktop.
Okay, give me a second.
Yeah, no problem. Now we are all right. Yeah.
Okay.
Maybe you want to go on full screen.
Yeah.
And then we are perfect. Yeah.
Yeah. Is that fine? Can you see that?
Yeah. We can still see the outline on the left, but it's okay. The slides are clearly visible. Thank you.
Yeah. So can you see this change in the slides?
Yes. Absolutely
okay.
Fine.
Great.
Thank you.
So should I start then?
You're most and welcome. Thank you very much.
Okay. Thank you. Okay. Thank you, everybody, for giving me an opportunity to speak here. And today's topic is machine learning, spin system, and statistical mechanics. So I'm a member of School of Physics, Witwatersrand University. Now, before I even start speaking, so this is a school about machine learning and high energy physics. So high energy physics generally is really a broadly defined subject. So technically speaking, statistical mechanics may not sound like which is something which is part of high energy physics. However, as it turns out, spin systems and their study is somehow motivated by high energy physics in a way that we'll see soon that spin system has certain kind of continuum limit through second order phase transition, and the continuum theory is defined by quantum field theories, very similar to quantum field theories actually discussed in various branches of high energy physics. So they have a very close connection. The spin system and the study of quantum field theories are just the two sides of the same coin. And what we'll talk about today, this is the first talk, we'll just give you a generic introduction of what is going on, and I won't focus that much about the particular works I am doing, but roughly tell you that what community is doing, and in some places I'll also tell you what exactly I'm doing. And first, for first 15 to 20 minutes, I'll give you a very generic introduction of the problems of machine learning and how can they be used in physics, etc. And the second part, hopefully, second part of the school, I will be more pedagogical in a way that in the second part, not in this lecture, but in the second lecture, I'll try to teach in real time that how to code a simple machine learning problem and see certain patterns which possibly I'll discuss today in this lecture. So let me start. So what is machine learning? First, let us talk about that, and then I'll go to discuss about generative models. So various of my collaborators, Robert de Melocos, Chuin Mosmano, Zaid Zaz, and Pranav Rai are involved in various project and few other people. So thank all of them. And what is machine learning? So for example, machine and why do physicists care? For example, nowadays we hear various cool things that has been said. For example, there is a system which is proposed, which is called PIN, PINN, which is acronym for Physics-Inspired Neural Network. What it does is that if you give it any physical system, it will find the necessary differential equation from the physical system. So all the things which Newton has done, that is, he saw that there's the apple falling, and look at the data gathered by Kepler, Tycho Brahe, etc. And from that, he found out the laws of gravitation. It seems that this network has been claimed that given this data, the similar kind of data, this network can also find the laws of physics, for example, gravity or whatever that is correct differential equation that is governing the system. So these networks can find. Apparently, that's the claim. Maybe not 100% solid as it stands, but it is true that in very simple system, it does find the differential equation. So we see that there is a close connection between neural nets in a way that I'll discuss what we mean by neural net. As you can see that we'll get back to the same question again and again, but there is a block which is by colored somehow blue or something, which is called NN, some weight W and B. So, so this is an example of a neural net. We'll discuss what it is, but it has two parameters, weights and bias. We'll discuss what is meant by them. Because you can see that it is a very typical structure. So it has layer one, layer two, and then some input is coming, which is possibly x and t. So in physics problem we always have this positional data and the time data. So a particle is moving at what time, which position it is in. So this data is coming to this network, and now what this network is doing, it is giving some output u, and from that output we determine what is the Lagrangian, etc. But generically, you can see that basic concept of neural network is clear from here. It is just a generic function. What is doing is that taking some input and giving some output, and it has this very spatial structure. So there are layers in neural network, layers after layers after layers. It can have many layers, which is called deep neural network. But basically what is doing is that there is some arrows that has been drawn. And I'll discuss this strength of this connection between this block and this node and this node is determined by some kind of weight. So there is a weight matrix which determines how strongly these two nodes are coupled. And this there is also a parameter called bias, which sits in each node and determine how this node how function or how these nodes will turn on. So we'll discuss these things. So here, when you go to the neural network, what happens is that there is an input, and input is, as I have just discussed, some function of x and t, and then there is some weight. Weight means that, so say some input of X or something is coming. So what part of X is visible to Uj? So that is given by Wij into Xi. So Wij into Xi, that part is going to the Uj. And what is Uj is doing? And then there is a bias there. And what each node is doing is that there is an activation function. What is an activation function? That if, say, activation function is like a tan hyperbolic function, which is called perceptron or something. So this function get activated means that its input, whatever, so it is getting omega ij of this x, omega 1 of this x, omega 2 1 of that. So it getting contribution from all of this, and then there is a bias. You just take a linear sum of all these things, and if this thing is positive, that point this gets turned on and gives an output 1. If it is negative, it shuts down. So this is called activation pattern. So some of them get activated, some of them get shut down when some input comes. And now the output should match with whatever desired output you may have. And that way we optimize this parameter omega eigen bias so that given an input we get the desired output. And that process is called learning. So goodness of any fitting is governed by an error. We update the parameters so that this error, which is the output of the neural network, and its comparison with uh, the output given, and that part should be minimal. And that's what it, how we train this network and optimize all those weights. So this is a generic principle by which we train neural networks. And neural networks are just general functions. They're nothing novel than very generic functions. Okay, now, but before moving further, let us just broadly understand what is there in machine learning. Just now, what I have determined, what I have talked about is called supervised machine learning. I said that what machine does is that machine is a black box where some input comes. Black box means, as we have seen here, so even if we don't understand what is there, irrespective of that, machine is a black box in the sense that some input comes and some it gives some output, and we optimize that output. We already know what is the desired output, and by that method what we do is that we optimize all the weights to get a particular output. So this kind of learning is called supervised learning, where we have a training set for which we actually know the desired outcome and we optimize the machine to do so. And now, but that's not all. In general, there are other kind of learning. For example, one big area is called unsupervised learning. It's much more harder, in a much more hard, in a way that in humans generally do a lot of, or any animals for that matter, generally do a lot of unsupervised learning. So their learning is generally not supervised. So when you are doing a new task, you often, sometimes you know how this task, the optimal task could look like. For example, you are playing a guitar, then you know that how to play good guitar. So that's more like a supervised learning. But sometimes you are in unsupervised territories. For example, you went to a new city, you don't know what is there. You are just traveling and learning and seeing patterns that you are roaming around, say, in a Japanese town, and you see that, oh, these guys eat sushi. You come back to America, you see, or South Africa or some other place, you go to India and say, no, 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 these guys are eating burger. So, but nobody has told you that that's the pattern you should find. So human beings quickly learn various unsupervised patterns. So one big challenge is to somehow teach the machine to do some amount of unsupervised learning. And then there is another branch which is called reinforcement learning. So what is the reinforcement learning is that reinforcement learning is machine in each step. What it does is that, say, for example, various game of AI game, real-time decision, robot navigation, learning task, skill acquisition, etc., where the machine does various random actions, and and if the random actions actually achieve the goals, then this part, some of this thing is means that parameters then actually got, means if a random action is good, so machine will shift a little towards that parameter, means parameters are adjusted on that direction. Now it does another random action. If it is good, then parameters get adjusted a little bit towards that direction. That's why to reinforcement, the machine learns. So this is reinforcement learning, as you can see, is somehow halfway between supervised learning and unsupervised learning. In reinforced learning, the rule of the game is present, but it is not clearly said that, and it is also being said what is it may or may not in certain situation be clearly stated how to win a game. Those rules may or may not be clearly stated. The job of the machine to find both the rules which will make the machine win, and what is the bigger implication of those rules in this gameplay. Now, this is used, for example, in chess, etc., recently with great effect. So Google has new Alpha Zero, which can learn from ground zero through reinforcement processes and can defeat all other chess, not only human chess players, but all other machine chess players, even the best machine chess players like Stockfish, etc., which were designed by humans. This reinforcement learner is not designed by human. It is a virgin neural net which just knows the rules of chess, and it plays and plays, and through reinforcement it learns. So this is so we have supervised learning, unsupervised learning, and reinforcement learning. Today we'll be more interested in supervised, both unsupervised and supervised learning, and we'll discuss how we implement, etc. So learning generally the question, is it a glorified model fitting? Means, as I'm saying, that learning means there is a black box, and then this black box you are optimizing the parameters so that you get the desired outcome, or you learn some unknown pattern, but whatever. So this is very much like just fitting the statisticians do. So is it just a glorified model fitting? It is, but the thing is that the idea is that, so some people ask, what is so great about neural network? So there are two things which are great about neural network. It is a model fitting, but model fitting, it turns out, is not itself a trivial problem. In a way that that's all we have. Means if you can fit model well, then you can do whatever you can. And that model fitting is more like a more mundane term for deep learning. So generally, when you're learning something, so some challenges are there. Dimensional reduction. So in these neural networks, as you see, has a lot of parameters. Means all those links carries parameters, and now it becomes an impossible task for these networks to. So from this large number of parameters, we have to reduce to a small number of parameters. And this whole business is extremely nonlinear because we have perceptron at each nodes, and perceptron is a nonlinear function. So we'll discuss that. Sometimes we are going for the probability distribution, etc. But so this is some link with StatMech. So you can see that through machine learning, we have generated all those faces, which looks completely real, but these are all artificial faces, and there is no such real human beings. Okay. So similar things has been done. Just to give you some cool example, this is style transfer. So some kind of modern photos has been style transferred to some old school European painting, etc., like Van Gogh, Monet, etc. And there are deep fake that the gender of a person and the face of a person could be changed. So one reason that neural network run so easily is called because of back propagation. So there is something back propagation means that when you get some error at the last level, there is some ways to back propagate that formula, and generally fitting something is very hard. I'm saying that you have to optimize all those omega I parameters, and but there are many more of them, and to optimize each one of them, each parameter, you need a derivative of the error function with respect to that parameter. So if you have this n square number of parameter, because all the nodes are linked, so you have huge number of derivative calculation, and it is impossible to do that many derivative calculation. It seems that because of how neural networks are constructed, that in each node we just have a linear combination of the previous, what is coming from the previous nodes. It turns out that all we need to to basically need is just the derivative computation with respect to each node, not with each link. So that method is called back propagation. So writing any kind of link derivative in terms of the node derivative is called back propagation. And fortunately, for this kind of network which is linear, and then some function is applied on the linear combination, for those kind of network, this back propagation tricks works. Well, it doesn't always work optimally, in a way that the optimization that back propagation inspired algorithm will give may not be the best solution, but at least to some extent that this works. Okay, so before that, so we'll talk about, does feature extraction has, so what network does is that, as we have seen, that it takes complicated pictures. For example, here it changes from one dog, take this dog picture and changes it to some kind of old means painting style, etc. For example, this is, I guess, is Van Gogh, from this lion picture to this picture. Now, what happening is that this kind of style transfer is not a random injection of some style in this picture. That would not work. This network has to understand various things about what are the objects that have appeared. So I think this is a Picasso style, sorry, and this is Van Gogh. So for example, this picture, so this starry sky picture, so it has to understand that what this picture means to do a successful style transfer. You can't really randomly inject ingredient from this picture and this picture, then this whole picture will be destroyed. So for example, this neural network has understood that it has to keep this dog intact when it is doing the style transfer. So it is actually the picture of the dog. These are water drop or something, or bubbles or whatever, and in some extent that has also to be preserved. So these understandings are necessary for this network. So basically the network extracted some feature from the picture. And now in physics, we have something called renormalization group. What does renormalization group does is that once given a physical theory, renormalization groups tells us that what are the quantities that is important at larger scales. So renormalization group actually does some kind of rudimentary feature extraction. So what this neural net's doing, does it have anything to do with what physicists call renormalization group? Yeah, And so what kind of features are extracted by RG is that features, say long distance modes are some kind of features in quantum field theory. We'll discuss that soon, I think, in the context of spin model. So there are various ways, both supervised and unsupervised ways, to concretize this problem, that what is neural nets doing? Are they similar to what physicists call renormalization group? I- And in renormalization group, we have a well-defined way of extracting feature out of a complicated spin system, and features are basically long distance mode. Um, However, given a generic neural network, is it also doing something similar? Now, this problem is not a well-defined problem, and it's better not be a well-defined problem, and because it is not exactly a mathematical problem like, okay, this we can prove this neural network is like RG. It is a more deep problem where what we are striving for is actually we're trying to understand in what way feature learning has something to do with RG. So first, let us look a little bit at unsupervised learning. And if time permits, today we'll talk a little more about supervised learning. So one good class of unsupervised learners are called generative model. What they do is that given a statistical distribution, they want to generate that statistical distribution or a probability distribution. So one class of probability distribution that is encountered in physics is the thermal statistics of a spin model and its partition function. From those quantities, we get a probability distribution. Basically, thermal, anything when you call thermal, that basically means that it has various probabilities of, of being in various places. Means that we'll discuss soon that something is thermal. For example, we'll let us talk a little bit about a very popular spin model, which is called Ising model. It's very well known to physicists, but let us still revisit it. So Ising model is nothing but a lattice, and in each side of the lattice there is a spin sitting, and the spin can be up, denoted here by red spins, and it can be down, denoted here by blue spins. And there is certain kind of interaction between these spins. So interaction is given by Si plus 1. Si plus 1, generally what we mean is that one spin is actually interacting with its neighbor. And if this is 1 and this is 1, this is minus 1, and 1, the energy of this configuration is multiply the spin values in the neighboring regions, and you sum them up. And that is how you get the total energy of the configuration. For each links, just multiply the spins which are sitting on the other end of the links. So what happens basically is that if we do that, and that is the Hamiltonian of the Ising model, then from that Hamiltonian, what we do is that we define a partition function. So e to the power minus beta into h is the partition function, and beta is the well-known inverse temperature. You can also introduce a magnetic field here. That is, you can bias the spins. That is, you can say that, okay, red spins internally have more probability than blue spins. That also you can do sometimes, but in most of our examples, we keep h to 0. So what does this kind of partition function means is that this is basically a probability distribution. Thermal means that we are not talking about just one spin configuration. We are talking about a collection of all possible spin configuration. And there are many. If the lattice side is L square, there is 2 to the power L square number of spin configuration. Now each of the spin configuration has their energy, and we get and we say that probability of getting one spin configuration is given by e to the power minus beta h. But generally what we see is that as exponential function is convex, etc., you'll see that low energy configurations always have more probability, and high energy configuration have low probability. So it looks like means a very kind of simple problem. We just have to concentrate on low energy configurations to learn more about the system. However, there are two things. Low energy, if we fix total energy, say we fix total energy to say zero, or the lowest value, then you just have actually one configuration. All the spins are in the same direction, actually two configuration. All the spins are red or all the spins are blue. But as you increase the amount of energy, you will get many more configurations. So if you will look at an energy 100, then you will possibly get millions of configuration which satisfies the relationship that total energy is 100. So as we increase in energy, we get more and more configuration, and that is called entropy. So higher energy states has more entropy internally. So what happens when we do this kind of e to the power minus beta kind of summation? If value of beta is large, then all the higher energy states are generally cut off, and we'll get a physics which is governed by the low energy state. But if we reduce the value of beta, this entropy will dominate at some point, and the nature of physics may drastically change. Okay, what is C? So if we look at the magnetization at each temperature, magnetization is nothing but the average value of the spins. Means you look at all the side, you add up one for the red and minus one for the blue, and sum this up. So what is the average value of the spins? And that was what we call magnetization. So as we change beta, so this thermal average means this probabilistic average. So I'm just now I said that magnetization is average for one given configuration, and given that one value, you can now weight it with e to the power minus beta h. That is, you can calculate what is called this expectation relative to this probability distribution. So you just take one configuration that's and its magnetization, and multiply it with its weight and sum it over, just do the regular things, and find a average magnetization over all the configuration. So average magnet, and this average magnetization will be function of temperature, and lower the energy, lower the temperature or higher the beta, what we'll get, and most spins will be in the same direction. So we'll get a high value of magnetization. As you can see that magnetization is pretty high at low temperature. Now as we increase the temperature, we expect the magnetization to go down. But now what happens is that, for example, when the temperature is near 2.26, something drastic happens, which we haven't expected. We're just expecting that magnetization will go down and with temperature, and that's pretty expected. But now we suddenly see that entropic state starts dominating over energy minimization, and magnetization not only gets reduced, it just becomes jumps to zero. So there is a strong non-analytic behavior in magnetization. It was positive at some point and it's coming down, and then it suddenly becomes zero. And this is what is known as phase transition. Phase transition. And it's a very popular subject in physics. Some part of statistical mechanics is built on that, and a large part of it. And you can get phase transition in various other models. You can have dynamical phase transition. This is an example of second order phase transition. So magnetization suddenly becomes zero and entropic state starts dominating. For example, if you look at the red-blue configuration in a big lattice, then for T less than Tc, you will see big region, chunks of spins which are aligned in the same direction. And higher temperature will see a complete dominance of entropy. None of the spins are almost aligned. So what happens is that if you look at the spin-spin correlation here, the spin-spin correlation is finite. However, what happening here, these finite size regions actually expand at t is equal to tc, and they somehow becomes infinite size, and this is the phase transition point where spin-spin correlation has infinite range, and it is scale invariant very interestingly. So if you scale this graph, what will happen is that you'll see that these regions will reduce in size, but here these regions would not reduce in size. This region becomes completely random, this region becomes uniform under scaling, this survives under scaling. If you scale it, it will still look the same. It has a fractal property. So this is what is called phase transition in physics and in spin model. So point to note is that we can have next to nearest neighbor interaction. What is called next to nearest neighbor interaction is that in this model we're just talking about points which are sitting next to each other, and they were interacting. But you can have a long distance interaction. Point here can interact with point here, here, and there, etc. So creating a sign called a long range interaction. And if we turn on next to nearest neighbor interaction, so the second next to nearest neighbor interaction, then what happens? The phase transition, the nature of the phase transition looks almost the same, but the phase transition point is shifted in the right, shifted to the more, you need more temperature to achieve the same amount of phase transition. Okay, now we want to learn a little bit about Ising model through conventional neural network and through some kind of generative model which we'll call RBM. So what is RBM? As we discussed, the conventional neural network which does the classification, that is you give it some input and it tells is good or bad. Here are extract features, which is also a kind of like complicated classification. Is that given a picture, it tells you that whether it has a dog face or a human face, and if it is there, where it is there, etc. So it gives information, extract features, and classify. Now, this doesn't directly generate any kind of probability distribution. Now, RBMs are generic probability distribution generator. So they also looks very similar to a generically a neural network. So we have same visible layer and the hidden layer, we have bias, we have activation. So something comes and goes through all those visible layers, comes out of the hidden layer and does all these things. Now, what RBM does, unlike the neural network, has two-way connection. So what you give some input to visible layers, it turns out some amount of the hidden layers, and these hidden layers will somehow determine what kind of input layers, and they are in turn connected with the input layers and determine what will happen to this visible layer. So there is a both-way connection as it happens in physics models. So probability of a hidden layer will turn on given a visible layer is given by same kind of activation function. And probability of the hidden layer will be turned on given a visible layer will be turned on given a hidden layer is given by similar kind of another kind of set of activation function, basically with the same weights, because weights goes both ways. So how these models are defined, but possibly with different bias. Sometimes you just takes these biases to be zero, so no complication coming from bias. So how do we train this kind of RBM? What we do is that we take some configuration of the visible layers, some spins, say 0, 1, etc. And then what happens is that that turns on and or off some amount of hidden layer. And these hidden layers then used to again turn on these visible layers. And given a visible layer, what you are doing is turning on hidden layer, and then again you are getting back what this visible layers are talking about. So this method is called reconstruction. That is, you have some kind of visible layer. From visible layer to you go to the hidden layer, and this part is from visible to hidden is very much like a neural network, so it is half neural network. But then this neural flow is turned around. You are going back from hidden to visible. In the neural network, in the supervised learning kind of generic deep neural network, we go in one direction. There is no getting back. But RBM in the second step is getting back, and again reactivating the visual layers. So from visual layer 1, hidden layer, and then visual layer, that process is called reconstruction. That is, you get a visual layer, from that you somehow turn on some amount of hidden layer, and then again get another set of visual layers. Now RBM is optimized by demanding that this visual layer should be equivalent to that the sake of its reconstruction. So basically what you want to do is the distance between a visual layer and its reconstruction should be reduced, and that's how RBMs are constructed. And given a probability distribution, when you say that RBMs has learned this probability distribution, is that we generate various combinations of the VIs. And what are the VIs here? VIs are just these spins. So spins in the spin system, which has been drawn here also. So you have thousands of spins. In most cases, like few 40 class 40 lattice, that's what we work on. So it may have something like 1600 spins or something. So all those spins are fed into this RBM, and it has learned something. And then in the next step, it is again reactivating the visual layers, and we want the spin configuration. When we say that this RBM has learned this spin configuration, is that mm, basically the input we give and the output we get look similar. Now look similar, then you may say that what is the point of even this kind of learning? uh, if you can just so learning means if you can identically, if these two are identical, then you can just use that. Why bother to learn? But learning, why learning is necessary, what has been learned here basically is that you have a few number of spins here. So this system is going through a bottleneck. And when the system is going through, and bottleneck is an important concept in learning, whenever the system is going through the bottleneck, then so there's a lot of information here. So these few hidden layers has somehow filtered out the good amount of noise, and so good amount of noise from here, and only keeping hopefully the relevant information which can be reconstructed in a visible layer. And then the trick is that once the learning process is done, all these weights are optimized, then this RBM becomes just like a generator. So you can then ask RBM to randomly generate spins, and this RBM will draw from the distribution of these VIs. So now we can do the same thing. I'll go a little fast here. So what we can do is that we can show these RBMs as we had discussed. The input from the spin system. So we look at some kind of RBM, and then we feed them various kind of Ising model picture. In place of red and blue, I have drawn these pictures with white and black. And when that happens, that at some after some time, the spins this RBM learns this distribution. So the question arises that okay, that's very interesting. That what has it learned? So what has been learned is very interesting that so given a spin system, if we look at the reconstruction, we get something very interesting that this reconstruction looks very much like RG in a sense that if we take a large number of spins and put them in a small number of hidden layers, so these are say small number of hidden layers, so some these blacks are say hidden layers, some small number of hidden layers. So what we get back looks very much like RG. So successive reconstruction looks like a renormalization group flow. And there is some very interesting work on that direction. For example, done by my colleague Robert de Mello Koch and many other people who did work in the same thing around the globe. So they have studied this RG flow coming from RB. I'm also working on that, but in a little different thing. So RG flow coming from this successive reconstruction. And it seems that this successive reconstruction leads to some kind of RG flow, and that they are trying to understand. And it seems that, and something very puzzling happens. If you look at the Ising model, we know that it can live in various phases. For example, this is called ordered phase, this is called disordered phase, looks completely random, and this is called critical phase. So what happens is that very interestingly, if you just show this Ising model pictures from this disordered phase, but not in one temperature, but say these are all the disordered phase. You take few temperatures here and feed the Ising model data from all these temperatures, but do not show this Ising model any data, means do not show this RBM any data coming from the critical temperature. Then also, very interestingly, this RBM learns a lot about critical temperature. Then also RBM learns features which, and then also you haven't shown the RBM, the critical temperature at all. You have only shown one region of the phase space, that is this region. But even then the this kind of RBM learns about criticality, and RBM flow, that is reconstruction flow, becomes very much like RG flow. And that happens in one-dimensionalizing model, two-dimensionalizing model, and various other things. Okay, so maybe for today, we already have spent some time. Maybe I'll stop here and invite questions. I have some other topic that how to actually code some RBM and see some of those pictures. That will be the topic of the next lecture maybe. But maybe in 2 minutes, I'll just discuss another way of looking at various things. Unfortunately, we don't have a lot of slides on that. So what we are also studying, so I have just said that I'm studying RBM, but with RBM, basically in the place of, in the RBM scenario, we're studying the effect of small RBM and how it generates probability distribution, etc. A little different than this large RBMs which has been used in spin system. But here what we are doing something else with conventional neural network, not a generative model. Conventional neural network is this the new works with one-way flow, which just extract features and classify things. So what we did now is that we taught a network as it extract features the notion of criticality. So we have fed it this Ising model phase diagram and told the network, look, uh, this part is called critical. So whenever you see from, and it doesn't see this magnetization curve. What it does is that it just sees the spin configuration. But since the this spin configuration which are coming from this region is called critical. Now what I do is that I do, so we train the network from this the Ising model data points, well-known Ising model data points. But then we turn on various kind of next to nearest neighbor interactions. So when you turn on next to nearest neighbor interaction, this is g is equal to 0.1, this is g is equal to 0.5. Then we ask this network to class. So this is a magnetization look. So this is the saffron curve has been drawn in red here. So what happens is that even then, the network can find out these critical points very well. And even if we turn on magnetization and does various tricks, so one criticism is that it just understand that when the magnetization is near half or something, then this is critical. No, even if we change the value of magnetization by introducing magnetic field and by hand and doing various other things, the network still robustly can find out that there is a critical region, and when it sees the critical point, so this network learn about criticality. So we haven't put it out this work yet, but we are kind of writing it down, and hopefully soon do it. And in various other spin models, we are trying to teach the network that there is a distinct definition of criticality, and machine can't only classify high temperature, low temperature phases, which has been done by other people, but it actually can learn just by looking at various spin configurations. There is a special class of spin configurations which are critical. So learn more about physics really. So that's where I'll stop today. And in the next lecture, maybe I will show you how to do some of these things just for students, how to write codes, etc.
Yeah, thank you very much, Palak, for the very nice introduction to methods of machine learning and their use in a statistical physics setup. Let me see, Ilya, have you seen if there are any questions of the participants in the chat or in the Q&A?
For now, I don't see any questions. And, maybe I can ask. So, like,
You're most
kind of,
welcome.
sorry, Palab, because kind of to the best of my knowledge, kind of the works when the people are trying to find, like, for example, critical points for the spin model with help of RBMs have already been present, like people have done it. Have you done it for some other statistical physics model, like, for example, for the POTS model and kind of which are not directly like a spin models, but I mean, somewhere in the vicinity of those?
No, we haven't yet. But the thing is that one low-hanging questions could be means that which can be easy to solve is that forget about spin model. Potts model is also a spin model, but anyway, I understand that's a very interesting question you have asked. So not maybe it's the Potts model, but there are other models, for example, percolative models, so percolations. And then there are models like TASAPE, ASAPE, where the criticality is more dynamical. So this is a low-hanging question. Means even with the current technology, one can answer this question and one can teach the machines very quickly. Means we can set up these problems very quickly, and this is the unexplored territory. And it's a very good suggestion that means one should study these things, and it's won't be that difficult to study this thing. But there are various other models which are not spin model. And I exactly had this question because people are putting too much energy on spin models. So the question is that what happens to the other models? Why not study something else? And there are thousands of different models like percolative model, dynamic models of dynamical criticality, which can also be studied using RBM and machine, etc.
Okay. Thank you very much. And I still do not see any questions from our participants. And maybe, I can ask one more question in the
Please.
similar spirit, because like, again, like, kind of like standard Ising model is kind of relatively well studied, but kind of
Yes.
what about like, even in 2D, but I mean, quantum models which exhibit some phase transitional behavior. We're not talking about, like Heisenberg or Ising models, but maybe, was the Hubbard models or Fermi-Hubbard models. Do you think that RBMs will be equally efficient for those classes of models, identifying the phase transitions and kind of the phase diagrams?
Right. Means that no means that if you look. for example, RBMs are not yet, I would say that are not that successful in even describing the phase transition of Ising models. Means there is a curious fact that, as I've just discussed, that if you teach it in some region, it somehow learned about criticality. So what
Mhm.
I didn't tell you is that this is wrong. Basically, it cannot happen. Basically, we know that reconstruction flow actually exactly reproduce the distribution you have you kind of fed the IBM. For example, if you sample data points from these regions, I'll answer your question. I'll come back to that quantum models. But
Mhm.
let me tell you that in a quantum way, we haven't yet solved Ising model yet. That if you sample data points from here, some will claim that it has learned criticality. No, that cannot happen because if you sample data points from here, we actually learn about the distribution which is coming from here, not about the criticality. That can be proved analytically. That's what RBMs do, or analytically or semi-analytically. Now, what happens is this is somehow a little involved question because if you read, so the thing is that you are taking this 1600 spins, but feeding it to RBM with 100 or 80 lattice points. So this is important that you feed it to a lattice point with sufficiently low number so that it only understand the large scale features, not the small scale features. So those things are not very well understood in what, and if you take too many of these hidden layers, then you get back the distribution exactly. Then there is no RG, nothing. So it has not been clearly understood, in my opinion, that we don't yet understand that what is this dimensional reduction that is going on in preserving these critical features. So that's answer number one, in a way that we don't understand this RBM Ising model connection very well. Although many people have worked on it and wrote a lot of papers, but we still don't understand these things. Okay.
Okay,
Now,
okay. Thank you.
second
Good,
question.
good, 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 good to know that because yes, just from the reading the archive, one gets an impression that, you know, everything, at least for the kind of the typical Ising models, I don't know, in 2D, it's all done and dusted, and people are looking now for the more the general
No,
solutions.
no, in a way that this kind of question that it is very ad hoc and arbitrary. You take, say, 1600 to 100 and you extract some properties of the critical model and you claim that it's critical. And as Robert has shown that many other things, actually, even if you just follow the procedures of those works you are talking about, so you will see that what happens is that many other things are not satisfied. For example, Robert looked at 2-point function, and he has shown that that part RBM actually doesn't correctly reproduce the critical 2-point functions. So you get some other value. So only the magnet, some part, in some quantities, the RPM calculations and some configuration does look like critical. So it's not a generic thing that everything will become critical. So those puzzles hasn't been solved. So this connection is very tenuous. Um, that in what way RBM is learning the critical points. And I think that there is also not clear understanding that what kind of data should be fed to the RBM. Should we feed, feed the high temperature data or just the critical data? So that point also is not very clear. So some people say that if you want the machine to learn criticality, we'll teach directly the critical data. Fine, but that's kind of not like a very telling problem. So it's a complicated thing. So I don't know. Now, to answer your question, now, if we look at the spin model, of course, there are Harvard model, etc. Now, means quantum model, sorry. So you can just do the same thing and try to learn these probability distributions. Another interesting direction to go is that somehow you use RBM to construct the ground state wave function in a way that you these probabilities that is coming from RBM. So you given a visual layer. What RBM does is that RBM calculates. So where is RBM? So what RBM does is the RBM calculates the probability of these things in certain ways. It generate these layer with some probability. So these probabilities can actually be used as the coefficient of this spin configuration in the ground state. And there are various ways. Some directly use the square root of the probability, or you can use some phase, etc. But in ground state, generally you exclude the phase. So that is another way of calculating a quantum wave function through RBM. So of course there are some works on that regard. I don't know how again successful or good in capturing the critical properties. Um, I don't know very well. I think not, but I think there are superficial claim that it does. But in none of these works is clearly understood. What is not understood is that if you given a visual model which is critical, quantum, classical, whatever, what does criticality means in terms of the hidden layers? What is meant by the hidden layer is capturing the critical information. Does it also become critical in certain ways? In what way then? So that part is not understood in any of those works. In my opinion, I don't know. I have to check in more thoroughly.
Okay. Thank you very much. And there is a question in Q&A from Camille. And is there a broadly accepted definition of what is learning?
What is learning? Well, what is learning basically is that given a task or given any problem, learning means that you find out certain patterns from that system, and then you call it learning. Learning basically is learning, means learning is learning features, or learning is actually find out some pattern from a probability distribution. Now how you use this pattern, whether you use it to better some given task, reinforcement learning, or use to fit some curve as in supervised learning or unsupervised, you just find the pattern. Whatever it is, finding those patterns from data is learning.
Okay, thank you very much. So I don't see any more questions, so I can give it back to Francesco. Thank you.
Yeah, no, thank you very much, Pallab, for a very nice lecture today, and in particular for showing us how short the step is from the basics to the more interesting research questions. So thank you very much. So I'm sure all our participants are very keen to hear how the are you right? Are you right?
Sorry. Yeah.
Keen to hear how the story ends next week. Yeah. So
Sure.
thank you very much,
Many
Pallab.
thanks.
Thank you, Ilya, for moderating the questions. And thank you to our faithful participants for being always with us. And yeah, and next week we will meet again on Tuesday at 2 p.m. on the same Zoom link. Yeah. Thank you very much, Pallab. It was really nice. Thank you. Thank you very much. All the best.